Hey everyone, Mr. Weiser here. Today we're going to be learning how to transform and combine random variables. Let's get started. This lesson is Module 2, Lesson 5 in my notes, and you'll find this in AP Classroom, Topic 4.9, or in the Practice of Statistics Updated 6th Edition, Section 6.2. All right, example 1. Suppose we roll a six-sided die one time. Let the random variable x represent the probability distribution. Note that each outcome from 1 to 6 is equally likely and thus has a probability of 1/6. The probability distribution is given below. Of course, we're all familiar with die, hopefully, and with each die, you have a 1/6 shot of getting any sort of number. What kind of shape would this distribution be? Well, it looks like they're all flat on the top, so we call that a uniform distribution. It's symmetric, but this is specifically a uniform distribution. Calculate the expected value of x. Well, the expected value of x follows a formula where we just multiply each value times its probability and add them all together. You end up getting 3.5. And since this is a symmetric distribution, you can see how 3.5 is smack dab in the middle of 3 and 4. So that would make sense in this context. Part C, calculate and interpret the standard deviation of x. Well, this formula is a little bit more complicated. As you might recall, what we have to do is take the square root of all this stuff inside, which is the value minus the mean squared times its probability, and add them all together. And you end up getting something equivalent to about 1.7078. Now, remember, you can use your calculator stat menu to get this value as well. Simply put the data in L1 and L2, go to stat, calc, one variable stats, make sure your frequency list says L2, second 2 will get you that number, and press enter a couple times and you'll have your mean 3.5 and your standard deviation 1.7078. Always recommend doing that even if you think you know how to do it by hand. Now, what if we added 4 to each value of the rows? What would the new mean and standard deviation be? And how would this affect the center, spread, and shape? Well, let's look at what's going on here. If we added 4 to each row, we'll have something like this: 5, 6, 7, 8, 9, 10, as opposed to 1 through 6. What that's going to do is it's going to shift the graph to the right a little bit. Notice that the spread hasn't changed. The mean is a little bit higher. In fact, the mean is just going to be 4 higher, so 7.5. The new standard deviation isn't going to change. It's going to be the same spread, so 1.7078, and the shape's exactly the same. It's still uniform. So adding really doesn't do much other than make sure that the mean is going to be higher. What if I subtract 5 from each value? Well, 1 minus 5 is -4, 2 minus 5 is -3, and so on. So again, you'll have a shifted set of numbers. It's going to go to the left this time. It's still going to have the same shape, but it's going to be a new mean. It's going to be lower. So you take your mean and subtract 5, you'll get -1.5. Standard deviation is the same, still the same spread. And the shape's still the same, still uniform. Instead of adding and subtracting, suppose we took all of your rows and doubled the value, multiplied by 2. What would the new mean and standard deviation be in this case? How would it affect the center, spread, and shape? Well, let's take a look. So 2, 4, 6, 8, 10, 12. It's going to spread it out a little bit more. So you can see a wider distribution, but it's the same shape. Now, the mean's going to be 2 times as much. So the mean will be 7. Again, that's halfway between 6 and 8. You should be able to look at that and tell. The standard deviation will be twice as much in this case because it's spread out twice as much. But the shape's still going to be uniform. So it's still going to be the same shape. That did not change, but it's wider. Instead of adding, subtracting, or multiplying, what if we took all our rows and divided by 2? Well, you can probably predict what's going to happen. All the numbers are going to cut in half. It's going to be narrower. It's going to be skinnier. The new mean is going to be half as much. So you just take your mean and divide by 2. Your standard deviation will also be half as much. And the shape's still going to be the same. So it's just going to be less spread out in this case. Let's go generic. What if we just have a formula? What if we take all of our numbers and multiply by 1.5 and subtract 3? How would that affect the mean standard deviation? Well, let's start with the 1.5. So if we multiply everything by 1.5, okay, that's going to spread it out a little bit more. It's going to multiply everything by 1.5. So if I subtract 3 from those, it's going to shift it to the left 3. So notice that it's not any less or more spread out than multiplying by 1.5. All we did is move it to the left a little bit. So what that's going to do is it's going to multiply the mean by 1.5 and subtract 3 from it. So that new mean is going to be 2.25. The standard deviation, however, only the multiplication is actually going to affect it. And you can verify all this in your calculator if you want to. The shape's still going to be the same. So the generic kind of thing about this is multiplying or dividing will always change the standard deviation and the mean. What it won't change is the shape of the distribution. Now, the only adding and subtracting will change the mean, but it's not going to change the standard deviation because all it does is shift it up or down. So you can pause and write this information down if you need to. Notice also that we in this little formula notes that I have here, the multiplication has a absolute value around it, and that's just because if you multiply or divide everything by a negative number, it doesn't affect the spread. Standard deviation is always a positive value, so we just look at the positive when you multiply or divide by numbers. All right, let's do some more die rolling. This time we're going to roll 2 six-sided die. Suppose we roll a die twice, find the sum. Using the sample space, let's fill the probability distribution, create a histogram, find the mean and standard deviation of the two random variables added together, x plus x. We're going to assume that these die are independent of each other. So one die roll has no effect on the other. Here we go. So let's look at our probabilities. Well, see if we add 1 and 1, we get 1 out of 36. That's the only one I can see there. We got a couple that we can do to get 3. You should be able to see a diagonal pattern forming here as we go through it. 7 is going to be the most common one. And then it kind of tapers down again as you go up until 12, which only has 1. So you can get all those probabilities in there. And you can put that in your calculator and get the mean and standard deviation. So let's do that. Just a little pro tip, you can put fractions in your L2. So if I want to do like 1 out of 36, I'd be able to do that. I just do 1 divided by 36 right there, press enter, and it'll put that as a decimal, but so you can go to the next one, 2 out of 36. You can put all those fractions in. I'll spare you the time here. Voila, they're all entered in. So we put our stat calc one variable stats to the test. I have my L2 as my frequency list. I'll get a new mean of 7 and a standard deviation of 2.4152. Let's remember those numbers. All right, so here we go. 7 and 2.4152 are my new mean and standard deviation of my combined random variables, which is both rolling one die and adding them together. I have my decimals there, so that way I can draw a nice little histogram and notice that it's not uniform, but it is still symmetric, centered around 7. All right, so let's look at a couple numbers here. How does the mean of x plus x compare to just the mean of x? Well, let's recall what the mean of x was. Remember, it was 1, or 1.7078 was the standard deviation, rather, and the mean was 3.5. I also added something called the variance, and the variance is the standard deviation squared. So we're going to utilize that today as well. So if you square 2.4152, you get about 5.833. So let's look at the mean of x, 3.5. Well, it looks like for the mean of them, it's just going to be added them together. So 3.5 plus 3.5 is 7. So that's pretty easy. Standard deviation. So let's see, maybe I add them together. So if I look at my standard deviation for x, it was 1.7078. So if I add those two together, I get 3.4156. Well, that doesn't match what I have over here. So if you look over here, my calculator said 2.4152. That's different. So something's not working here. Let's skip that and go to part C. How does the variance, which is the standard deviation squared, compare? So 1.7078 squared is 2.9166. Verify that in your calculator if you'd like. If I add those together, I get 5.833, which is my variance for my combined variables. So that ends up checking out. So that means that if I square root that, I'll end up getting the standard deviation. So it's interesting how that works. So again, looking at my calculator, the standard deviation for the combined sum was 2.4152. And if I take my 1.7078 and I square it, and then I do the same thing, 1.7078, and I add that together, I get 5.833. And if I square root that number, I end up getting what my combined standard deviation is. So it's a weird little trick, but that's how we have to work with it in this case. So let's try it again for subtracting. So now instead of adding them together, I'm going to subtract my die roll. So my first roll minus my second roll. So let's think my first roll is I want to get 1 minus 6 in this case to get -5. That's only one time, 1 out of 36. Then you can see another pattern forming along the other diagonal. 1 minus 5, 2 minus 6. And it's going to be a similar situation. If I put that in my calculator, I will get, well, I'll get the same probability setup. It's just that everything's going to be shifted centered at 0. So I'm going from -5 to 5 as opposed to 2 to 12. So I got those same probabilities here. Let's go into my calculation and we'll get our setup, L1, L2. One variable stats gives me a mean of 0 this time. And the same standard deviation as before, 2.415. Huh. Well, why did the standard deviation stay the same? Let's look at it visually. So we got our mean, we got our standard deviation, 0, 2.4152. If I graph all those, I'll get something that looks like the sum one. So this is the sum one. This is the difference one. Now look at the two difference. It's the same shape. Everything is exactly the spread out the same way. The only difference is one's centered around 7, while the other one's centered around 0. So let's compare. So if the mean is going to be, instead of 3.5 plus 3.5, it's going to be 3.5 minus 3.5. So as we make those comparisons, just think about that. Subtract those two. The standard deviation, well, subtraction doesn't work because there's a significant spread. It's the same spread as before when we added them together. So we can't just subtract them. And we certainly can't add them together because that didn't give us the same thing. Again, 1.7 plus 1.7 is 3.4. So that's not going to work either. So let's skip to our variance again. The variance is the standard deviation squared. And again, if I square the standard deviations of the 1.7078, add them together, I get 5.833. If I square root that, I end up getting the same standard deviation that my calculator is giving me on this. So even though I subtracted those two random variables, I still had to get a bigger spread. So I still had to add the variances, square root that to get the standard deviation. So the spread is going to be the same. It's just a spread out as before when we add it. So big thing on this is when you're combining random variables, you absolutely do want to add the means together or subtract the means together in whatever order they're doing. But for variances, we only add. There is no subtraction. Spread increases when you combine random variables, whether you subtract them or you add them. So you must do plus between them. For standard deviation, remember you square the standard deviations individually, add them together, and take the square root. Is there a formula that this reminds you of? You might think Pythagorean theorem, a squared plus b squared equals c squared. That is something very similar to that, although there's modifications to it for this problem. But yes, that's essentially what you're doing. You're squaring the two things, adding them together, and then taking the square root to get the new standard deviation. Can that work with multiple things, more than two? So let's look at 3 dice. Here's the distribution of that. I'm not going to sit there and try to figure all that out, but if you pause the video, you can look at the outcomes for rolling 3 dice for the sum. So we got 3 to 18. There's only one that gives you 3 and one that gives you 18 because either 3 ones or 3 sixes. Here are the probability breakdown of them. We're going to verify that the mean is the 3.5s added together 3 times, and the standard deviation is each individual standard deviation squared, added together all 3 times, and then square rooted. So if you want to try that, put it in your stat menu, use these probabilities and these sum of dices, and see if you can get the mean and standard deviation to work. You'd want to enter all 3 to 18 in here and the probabilities that go along with those specific dice. Go to your one variable stats and make sure L2 is in your frequency list. And if you look at the mean, it's 10.5 and the standard deviation is 2.958. And if you're going to calculator and add the 3.5s together 3 times, you get 10.5. And if you square 1.7078 plus 1.7078 squared plus 1.7078 squared and square root all that, you end up getting 2.9579. So this is going to be the same thing. And that applies for however many random variables you are combining together, whether you're adding them or subtracting them. The standard deviations are always going to be added in between the squared standard deviations, and then you square root them. Here's a little check your understanding. This is actually from a free response several years ago. Let's see if we can make some sense of this. So each full carton of grade A eggs consists of 1 randomly selected empty cardboard container and 12 randomly selected eggs. Suppose the mean weight of a full carton of eggs is 840 grams with a standard deviation of 7.9 grams. The weights of the empty cardboard containers have a mean of 20 grams and a standard deviation of 1.7 grams. It is reasonable to assume independence between the weights of the empty cardboard containers. And the weights of the eggs, it is also reasonable to assume independence among the weights of the 12 eggs that are randomly selected for a full carton. Let the random variable x be the weight of a single randomly selected grade A egg. What's the mean of the mean of x? What's the mean of the eggs? Well, so let's think about what it's asking. So we want x to be the weight of a single randomly selected grade A egg. So the mean of x would be the expected weight of an egg. So think about how many eggs we have in this carton. We have 12. And we know the mean of empty container plus the 12 randomly selected eggs combined together should give you the total weight of the carton, which we have. We have the mean weight of the carton as 840 grams. So you think about your 12 means, your empty carton, and your mean of the container is what it equals when they add it all together. So this is just means. There's no fancy squaring or anything like that. But we do want to maybe make our life a little bit easier and say 12 times the mean of the eggs plus 20 equals 840. Well, now we have an equation we can solve real easily. So when you're solving that, you want to subtract the 20, of course, and then divide by 12. And you get about 68.33 grams. So the mean's fairly quick to calculate. It's just an equation. Let's look at the standard deviation. The standard deviation of x, with standard deviations, remember we square each individual thing, add them together, and take the square root. So in this case here, we're provided the standard deviation of the full carton and the empty carton. What we're trying to find is the standard deviation of each egg, or a randomly selected egg. So remember, we have the 12 randomly selected eggs, and those are independent of each other. So we square their standard deviations, add them together. We got to also think about there's going to be a square root on top of it because we're going to find the standard deviation of the total full carton of eggs with the empty carton and the eggs. So we have to add that empty carton, also square that standard deviation. Fortunately, we know that. That's 1.7. And we want to set it equal to the standard deviation of the full container, which is 7.9. So this is the Pythagorean theorem on steroids. Basically, we have like 13 different things. We have the 12 eggs, and then we have the one empty carton combined together to give you your full carton. Add those standard deviations together, square root that, and you'll get the standard deviation of the full container. So we can simplify that. There's 12 of those individual eggs. So 12 of those standard deviations squared plus 1.7 squared under the square root is equal to 7.9. Now we can solve it, use our equation solving skills. So we want to undo the square root. We're going to square the 7.9. Then we can subtract the 1.7 squared from the 7.9 and then divide that by 12 to get the standard deviation squared by itself. Doing a little bit of calculator work, we'll simplify the top. So we have 7.9 squared minus 1.7 squared is 59.52. Divide that by 12, you get 4.96. And finally, we get our standard deviation of the eggs is the square root of that, which is 2.227 grams. So with linear combinations, basically, if you multiply anything that's a mean or a standard deviation, you you follow the multiplication rules. So if you multiply the mean. If you you know uh, in the standard deviation, what you want to do is you want to multiply prior to squaring if you are going to combine random variables. So if you're multiplying one mean or one standard deviation by a value, do that first, then square it, and then add the other thing squared as well. You could you could square the number that you're multiplying by, but I feel like doing that's a little bit too much. So I would do the first rather than the last. So let's look at the last example. Example 4. A large auto dealership keeps track of sales made during each hour of the day. Let X equal the number of cars sold during the first hour of business on a randomly selected Friday. Based on previous records, the probability distribution of X is as follows. One car sold, zero car sold, one car sold, two cars sold, three cars sold. We got our probabilities laid out. And the mean and standard deviation have already been calculated for us. So part A, describe the shape of the distribution, create a graph if necessary. So the graph would look something like that. That shape would be skewed right, peaked at one car. Now, suppose the manager receives a $500 bonus from the company for each car sold. We're going to let C equal the bonus received from car sales during the first hour on a randomly selected Friday. Part B, write a formula that expresses the random variable C in terms of X. Explain why the probability distribution of C and X have the same shape. Well, 500 bonus for each car, to me, that's multiplication. So we're going to do 500 times X. That's it. And it's going to have the same shape because when you multiply by a constant, it doesn't change the shape. So that's good enough explanation for that. All right, part C and part D, we're going to calculate the mean and the standard deviation. We're going to interpret the standard deviation. Suppose the dealer's manager receives a $500 bonus from the company for each car sold. Let C equal the bonus received from car sales during the first hour on a randomly selected Friday. Find the mean of C for part C. Well, we already have our formula, 500 times X, and we know multiplication straight up multiplies the mean. So 500 times 1.1 is going to be $550. With standard deviation, multiplication multiplies by the standard deviation as well. So the standard deviation is going to be 500 times the standard deviation, which is 0.943, and you get $471.50, $471.50. It does ask you to interpret it. So remember, standard deviation is the typical distance from the mean. With probabilities, you want to say if you randomly select many, many things, the the typical distance from the mean is going to be whatever our standard deviation calculated is. In the context of this problem, it would be something like this. If we randomly selected the first hour of business sales for many, many Fridays, the typical bonus would vary by about $471.50 from the mean. All right, now let Y equal the number of cars leased during the first hour of business on a randomly selected Friday. Based on previous records, the probability distribution of Y has a mean 0.7 and a standard deviation 0.64. It's safe to assume that X and Y are independent, so they don't interfere with each other. Part E asks you to find and interpret the expected value of T. So from the previous problem, or the previous part, remember we had a $500 bonus for sales, and then we have now, I'm getting ahead of myself. I'm sorry. The T is just going to be the number of cars leased plus the number of cars sold. So it's just add the two means. So What we're going to do here is we have our two means. We have 1.1 over here, and we have 0.7. So again, those are right here. The mean of x, 1.1, the mean of y is 0.7. So don't get too far ahead of myself here. Just simply add those together and you get 1.8 cars. It wants you to interpret that. So let's see, we're talking about Friday sales. If I were to select many, many Fridays for the first hour, the expected total number of sales and leased cars would be 1.8. So if we randomly selected first hour business sales for many, many Fridays, the average number of cars or expected number of cars sold and leased together would be about 1.8 cars. Calculate the expected standard deviation of t. Well, use that little Pythagorean theorem formula. We have two individual standard deviations. We have 0.943 and 0.64. We can square those numbers, add them together, and take the square root. Use your calculator. You get about 1.1397. And the last part. Now we're getting ahead of where I was trying to get ahead of. So in this case here, the dealership manager receives a $300 bonus for each car leased. Find the mean and standard deviation of the manager's total bonus B. So remember, he's getting bonuses from leased and sold cars. So with sold cars, it's $500 bonus. And with leased cars, now we know it's $300 bonus for leased. So let's think about what the mean and standard deviation is going to look like. Mean is going to be just multiply each bonus amount times the number of cars sold and leased, respectively. So 500 times the number of sold plus 300 times the number of leased. So that's just going to be 500 times 1.1 plus 300 times 0.7. You'll get about $760. So the combined bonus sales for a randomly selected Friday is going to be $760. Standard deviation, multiply those standard deviations first. So don't do the square thing yet. Take your 500, multiply it by 0.943. Take your 300, multiply it by 0.64. Then square those. Then you can take the square root after you add them together. So make sure that you do that multiplication first, then square, then add them together. You can do all that in your calculator if you type it in like this. You get about $509.09. Let me pause this for a minute here. I want to show you something. I'm going to show you how I key that in the calculator so I don't avoid mistakes, okay? So what I want to do is I want to type in the square root first. So square root. You can do second square root. And I'm going to do parentheses. We do 500 multiplied by, I forget what the number is, forgive me, 0.943. You don't need the zero, so 0.943 is fine. Then you're going to close it up, and then you're going to hit x squared. Then you're going to do plus. And then the other one was 300 times, was it 0.64? Yep. You're going to close it up, and then you're going to hit squared. Doing it like that will give you the right answer. There's your $509.09. The formula that your book will want you to do is do it like this. So instead of doing parentheses, it'll say like 500 squared times 0.943 squared. I find that to be too much typing. It's the same thing, but I'd rather just put it in parentheses because visually it makes more sense to me. But to each his own, you do what works best for you. And that's it for the examples on this lesson. Hopefully that makes a little bit more sense. It's a weird kind of situation with spread, but follow those formulas and you'll be good to go. I'm not going to really go over a lesson summary, but I'll just kind of display these again. If you want to pause and write any of this down, please do. And the key takeaway is make sure standard deviations don't get added. We square them, which is their variances. We add their variances. And then to get the standard deviation, you square root the sum of the variances. Thanks for watching, guys. Have a good rest of your day.